Welcome to another episode of Scientific Innovations Unleashed, where curiosity meets cutting-edge research. Today, we're diving deep into a topic that highlights both the potential of technology and the dark underbelly of scientific integrity. So, buckle up as we explore how we can ensure the authenticity of scientific results, specifically through modifications to a PCR machine. Let's start by laying the groundwork. You might be wondering, what's the big deal about a PCR machine? Well, PCR, which stands for polymerase chain reaction, is a cornerstone technique in molecular biology. It's used to amplify DNA sequences, playing a crucial role in everything from COVID testing to cancer research. But here's the catch. There have been instances where the data produced by these machines has been manipulated or fabricated. This brings us to a concerning reality in biomedicine: a lack of systems to verify that every article or result published corresponds to the raw data generated by lab instruments. For instance, imagine receiving a life-altering treatment for cancer based on flawed. Unfortunately, that's not a hypothetical scenario. Hospitals have treated patients with incorrect therapies due to dishonest research practices, resulting in significant harm. These ethical breaches highlight a systemic issue plaguing the scientific community. This is where our innovative project comes into play. We've set out to make scientific results verifiable and tamper-proof, specifically by modifying widely used PCR machines. Picture this. What if you could have a digital notary for your PCR outputs? That's essentially what we're striving to create. By integrating cryptographic signing directly into the PCR machine, any results it generates can't be altered post-creation. Now that may sound simple, but you might be surprised at the technical complexities involved. For example, the Thermo Fisher 7500 fast PCR machine, which is a standard in many labs, is notoriously challenging to modify. It runs on an old Windows XP application that relies on proprietary drivers. Talk about a technological dinosaur. Any attempt to adjust the machine's firmware could jeopardize its precise thermal controls. So how did we tackle this? Here's where things get interesting. We devised a clever workaround. We run the original PCR software inside a secured virtual machine. This environment is carefully locked down, preventing unauthorized access and modifications. The data flow is also designed to be unidirectional, meaning once results are generated, they can only move out of the system for signing and storage, ensuring their integrity. We've included a number of intriguing security features as well. Think tamper-evident resin seals, ensuring that any attempts to access or modify the machine are visible. Even physical manipulation leads to evident damage to the security seals, kind of like high-tech "do not disturb" signs. But here's an important distinction. While our system ensures the integrity of test results, it doesn't prevent issues like sample swapping prior to testing. We plan to address this in future iterations by implementing ways to verify sample IDs and document the testing process more rigorously. So you might be wondering, why start with PCR machines? It's basically because they are not only critical in research, but also frequently subjected to manipulation. We hope that this project serves as a blueprint for modifying other scientific instruments, leading to a future where results can be traced back directly to original instruments. Imagine having DNA sequencers that produce verifiable genomic data or clinical trial outcomes with guarantees of authenticity. It's a future we're excited about. As we wrap up today's discussion, the takeaway is clear. While the scientific community faces serious challenges in maintaining integrity, innovative solutions like cryptographically verifiable PCR machines hold immense promise. This is a pivota,